Next type of differential equations are ones where the derivative is equal to some function of y only. Now, of course, those ones we can easily do by separation. There's no dramas there. Just be careful, when you divide by the gy, you're not left with 0. You're left with 1. So you'll end up with the integral of dx is equal to the integral of dy on gy. Now, it is a type of first order differential, because if you moved that gy over, it would satisfy the requirements. So let's have a look at this, and you might actually recognise this equation. Oh, say it again. Growth and decay. Back when we were looking at growth and decay. But let's actually prove it, because you'll recall that when we did growth and decay, we were allowed to just quote the answer. So here we go. This is where it comes from. So we can now do it using our differential equations. So if I rewrite it as the integral of dy over y minus n equal to some constant times the integral of dx, we know the initial population is n plus a. So we match those up, and we're trying to link y and x in this case. So the right hand side, well, if I'm just going from 0 to x dx, we know that's x, but times a constant in this case. Left hand side, we'll have the log of y minus n. So kx is equal to, substituting in, we get y minus n over a. So e to the kx is y minus n over a, which means y minus n is equal to a times e to the x. And moving the n across, we get the answer that we're used to seeing. It also explains the trivial solution. Remember we talked about the trivial solution with growth and decay? Well, this is where it comes from, same idea. Because if I'm dividing by the y minus n, well then y equals n would be a trivial solution to that. Alright, so basically it was our modified growth and decay equation. But look, remember this is extension 1, and we said when we get a modified growth and decay question, we can just quote the answer. So there's nothing stopping us in that situation, unless they of course specifically asked us to derive it or something like that. Alright, let's have a look at this one. dy dx is e to the power of 2y minus 1. So I've divided by e to the 2y minus 1, but you'll notice using negative indices, I've written that as 1 minus 2y on the left hand side there. So we get minus a half, e to the 1 minus 2y is x plus a constant. And then, well, I'll make y the subject, so playing around with all that, eventually we get y equals a half, 1 minus the log of a constant minus 2x. The square root of 1 minus y squared. Left hand side of that is, that's one of our standard ones, isn't it? It's inverse sine or inverse cos, depending on what you prefer. I've got inverse sine. So inverse sine is equal to x plus a constant, so y is sine of x plus a constant. That brings us to what we call the logistic equation. It actually appears more often than you would realise. The standard form is this. The derivative of some function of x is equal to function x times 1 minus function x. That sort of pattern we're looking at. We're going to be restricted in our course to one simply like that. dy dx is equal to ky and then some p minus y. So it may or may not be 1. So let's do the most simplest of them all then, where it's y, 1 minus y. Okay, if we first look at the slope field of this, there's the slope field, and I've drawn in 3 possible solutions. Now, if a is less than 0, I get that orange one there. See, I'm going to have horizontal asymptotes there at y equals 0, but there's also y equals 1. They end up being horizontal asymptotes. Now, when a is less than 0, then it's going towards the asymptote underneath. When it's in between 0 and 1, it's in between the 2 asymptotes. And when it's greater than 1, then it's coming to the asymptote from above. It would have that sort of shape. So we have 3 solutions. Well, in fact, we actually have 5 solutions, because for this one, we would have 2 trivial solutions. It's the horizontal line of a equals 0 and a equals 1 for this one. Oh, not a equals 0, but where a equals 0, which gives us the line y equals 0, and when a equals 1, which gives us the line y equals 1. Let's go and find it. So dy dx is y, 1 minus y. We'll divide via partial fractions. I know that's going to be 1 on y plus 1 on 1 minus y. But of course, extension 1 don't do partial fractions. Well, it's not a terribly hard one. So you might see in an extension 1 question where they'll have a part where it says, show that that's the same as that. They might give a big hint or something like that. So the solution is the log. You can see I've combined it all into one straight away there, because I know we're going to end up with the log of y minus the log of 1 minus y. Combine it into one log. We get the log of y on 1 minus y. Substitute in y, minus substitute in a, but again I've combined that into one log straight away. And so we have log of that lovely expression. So e to the power of x will be, yes, it's lovely, isn't it? Y 1 minus a over a 1 minus y. Just to make life a little bit easier, because look, 1 minus a on a is a constant number. So remember, a is a constant. And then I'm going to multiply by that and get a e to the power of x is y on 1 minus y. That ends up with y equals a e to the x on 1 plus a e to the x. But I'm going to play around with that as well. I'm going to let b equal 1 on a. And then I'm also going to divide everything by e to the power of x. It just looks a little bit neater. So 1 over b e to the minus x plus 1. But don't forget the two trivial solutions. So y equals 1, y equals 0, or y equals 1 on b e to the minus x plus 1. Find any inflection points in the curve. Okay, we know possible ones will happen when the second derivative is equal to 0. So the second derivative is the derivative of the first derivative. So we're differentiating y1 minus y, because that's what we said the first derivative was. But we can't differentiate that with respect to x, so we'll do it with respect to y, multiplied by dy dx. But remember, dy dx is y1 minus y. Differentiating the first bit, write down the first if the second, write down the second if the first. Tidying all that up, we've got y outside of 1 minus 2y, outside of 1 minus y. So the question is, where are our possible inflection points? 0, a half, or 1. But hang on, we knew 0 and 1 were the trivial solutions, which are straight lines, there's no inflection points there, or they're going to be horizontal asymptotes. So again, there'll be no inflection points on those lines. So the only possibility is going to be where y equals a half. Y equals a half. But now we have to find the x value. So let's go back. And this is why we change the value, because I'm now solving b e to the minus x equals 1, but now I do need it in terms of a, because that's our graph, of course. So e to the x would be b, x is then log b, but if we work our way back, b is the absolute value of 1 minus a over a. Now, the slope field shows that there is indeed a change in concavity. So I'm not going to bother testing our possibility. So I can look at the slope field and say, yeah, okay, there is a change in concavity there. So therefore, that point of inflection is the log of 1 minus a over a half. 13D, playing with our logistic equation, amongst others.